In this lesson, we will discuss the Euler Phi function in more detail. Recall the definition of the Euler Phi function. We define phi of n to be equal to the number of positive integers less than or equal to n that are relatively prime to n. So the Phi function has been one of the central functions of number theory for over 200 years. Leonhard Euler was the first to study this function. That's why we name it the Euler Phi function. In 1763, he published a paper describing this function. But it was Gauss in 1801 who first used the notation phi for this function in his work Disquisitiones Arithmetica. Another name that is often given to this function is the totient function. So this name was invented by J.J. Sylvester in 1879, and he got the word totient from the Latin prefix tot, which means from many or many. J.J. Sylvester actually invented this word, so sometimes you might hear it referred to as Euler's totient function or the Euler Phi function. In any event, phi of n counts the number of relatively prime numbers to n between 1 and n. So let's look at a theorem that I alluded to earlier in the previous lesson. First, for a prime number p, phi of p equals p minus 1. So this part of the theorem seems pretty obvious because the numbers 1, 2, 3, 4, 5 up to p minus 1 are all relatively prime to p. But further, for any positive integer k, then phi of p to the power k equals p to the power k times 1 minus 1 over p. And if you multiply this out, you see this also equals p to the k minus p to the k minus 1. Okay, so those are kind of alternate forms of this formula for phi of p to the power k. So let's prove this theorem. Well, if p is prime, then 1, 2, 3, up to p minus 1 are all relatively prime to p. Thus, phi of p equals p minus 1. Now let's consider phi of p to the power k, where k is a positive integer. Well, there's the numbers between 1 and p to the power k, there's p to the k of them. Okay, so if we take all of the numbers between 1 and p to the k, and we subtract off the number of multiples of p, then the amount of numbers remaining will all be relatively prime to p to the power k, because the only numbers that divide p to the power k are multiples of p. Well, how many multiples of p are there between 1 and p to the k? Let's see. Well, number 1p, 2p, 3p, all the way up to p to the k minus 1 times p. Those are all the multiples of p between 1 and p to the k. So how many numbers are in this set? So there's p to the k minus 1. So phi of p to the k is p to the k minus p to the k minus 1. And if I factor out p to the k from both of these terms, we get the formula p to the k times 1 minus 1 over p. So this finishes the theorem. So now we know how to find phi of a prime or phi of a prime power. So the phi function is an example of a function that's defined on the integers. Okay, so the domain of this function is the set of integers. So we call these arithmetic functions. So the phi function is an example of an arithmetic function. Which is a function defined on the integers. Okay, another name for these type of functions is a number theoretic function. We'll call them arithmetic functions. So we will study more arithmetic functions this semester, but I'll first define what it means for an arithmetic function to be multiplicative. So an arithmetic function is called, let's call it f, is called multiplicative if f of m times n equals f of m times f of n, whenever m and n are relatively prime. So we shall see that the Euler Phi function is actually a multiplicative arithmetic function. The Euler Phi function is multiplicative. So let's begin the proof. Since phi of 1 is 1, it is clear that phi is multiplicative if for plugging in a multiple of 1. So it is clear that phi of mn will equal phi of m times phi of n when either m is 1 or n is 1. So let's assume that m and n are both greater than 1. and we're going to assume that m and n are relatively prime. Okay. And the key to proving this is to consider the array of integers that I'm about to write out. Then consider the array of integers so I want to write out a bunch of integers here. And the first row is going to be 0 through m minus 1. So 0, 1, 2, all the way up to m minus 1. The second row is going to be m plus 1, m plus 2, all the way up to m plus m minus 1. And the third row is going to be 2m plus 1, 2m plus 2, all the way up to 2m plus m minus 1. And then I'm going to continue down until the last row will contain n minus 1 times m, n minus 1 times m plus 1, n minus 1 times m plus 2, all the way over to n minus 1 times m plus m minus 1. So look at this array of numbers. See that in each row there are a total of m numbers. Okay, so there's m numbers in each row, and there's a total of n rows. So there's a total of n times m numbers in this array. And since these mn numbers are all consecutive integers, they will actually form a complete residue system mod mn. Okay. So there are mn consecutive integers in this array. So this array is a complete residue system mod mn. Okay. So think about these mn numbers. How many of them are relatively prime to the number m times n? Well, we define that to be equal to phi of mn. Thus, phi of mn of these integers. Okay, so phi of mn of these entries in the array are relatively prime to m times n. So we're going to count these relatively prime numbers in another way and show that this has to equal phi of m times phi of n. So notice that the first row is a complete residue system mod m. So let's look back at the array. The first row contains the numbers 0 through m minus 1. So this is a complete residue system mod M. First row is a complete residue system mod M. So if you look at the first row, it's a complete residue system mod M, and all the elements in any one column are all congruent mod M. Okay, so if you look at the entries in any one column, so for example, look at the first column, all these numbers are congruent mod M. They're all congruent to 0 mod M. Second column, all these numbers are congruent to 1 mod M, and so on. So the first row is a complete residue system mod M, and all the elements in any one column are all congruent mod M. Okay, so, and all the entries in any one column are congruent mod M. So in the first row, there's exactly phi of M entries that are relatively prime to M. So if in the whole array, there are phi of M columns consisting entirely of integers relatively prime to M. So there are phi of M columns in the array consisting entirely of integers relatively prime to M. And the other columns contain no such integers that are relatively prime to M. So there's phi of M columns containing integers relatively prime to M, and while the other remaining columns contain no such integers. So take a column of integers that are relatively prime to M. Okay. So what do these numbers look like? They look like, so its entries look like b, comma, m plus b, comma, 2m plus b, comma, all the way up to n minus 1 times m plus b for some b okay, and since the greatest common divisor of n and m is 1, since the GCD of n and m equals 1, we showed that this column must be a complete residue system mod n. Okay, so by a previous theorem, we can conclude that these entries form a complete residue system mod n. So let's just think about that for a minute. So think about the numbers 0, 1, 2, 3, all the way up to n minus 1. So that is a complete residue system mod n. So if I multiply by each one of those by m, which is relatively prime to n, and then add an integer b, then I still have a complete residue system mod n. From a previous theorem, we showed that. Okay, so then in each one of these columns, remember there were phi of m columns that had integers relatively prime to m. Each one of those phi of m columns is a complete residue system mod n. So in each one of these columns, there's exactly phi of n elements relatively prime to n. Okay, so that's the next thing we're going to say. So each of these phi of m columns so these are the phi of m columns containing all elements relatively prime to m. Each one of these columns contains phi of n, or entries, relatively prime to n. Okay, we know this because each one of these columns is a complete residue system mod n. Thus, there are phi of m columns, and in each column there's phi of n numbers relatively prime to n. So there's phi of m times phi of n entries that are relatively prime to m and to n. Therefore, there are phi of m times phi of n entries that are relatively prime to m times n. We know this because m and n are relatively prime. So the number of entries that are relative to both m and n are the same as the number of entries that are relatively prime to m times n. But we already counted these. We already said that there were phi of mn of these entries. but we already counted these entries as phi of mn by definition of the phi function. So therefore, we can conclude that phi of mn equals phi of m times phi of n, where m and n are relatively prime. Thus, the Euler Phi function is multiplicative. So let's look at a quick corollary of this fact that the Euler Phi function is multiplicative. If you have distinct primes p and q, then phi of p times q will equal p minus 1 times q minus 1. So you can see that if p and q are distinct primes, then they must be relatively prime, and we can write, so a quick proof, phi of p times q for distinct primes, p would be relatively prime to q, so phi of pq is phi of p times phi of q, and we know that phi of a prime is p minus 1, and phi of q would be q minus 1. So here's a quick example. Phi of 10. So far we've only had formulas for phi of a prime number or phi of a prime power. Well, 10 is 2 times 5, which are both prime. So phi of 2 is 2 minus 1, and phi of 5 is 5 minus 1. So phi of 10 is 4. And you could verify this. I mean, 10 is not a very big number. You just write out the numbers between 1 and 10 and cross out anything that's not relatively prime to 10. But now we can find a formula for phi of n for a general integer. So here's another corollary of the fact that phi of n is multiplicative. For n greater than 1, phi of n equals n times a product. So we'll use the Greek letter capital pi to stand for a product. So it's n times the product. The factors are going to look like 1 minus 1 over p, where p is any prime dividing n. So the product is taken over all primes dividing n. Okay? So you take n and you multiply it by a bunch of these factors, 1 minus 1 over p, where p is any prime dividing n. So here's the proof. So we're going to use the prime power decomposition of n. So let's let n equal p1 to the k1 times p2 to the k2 all the way up to pr to the kr for distinct primes P1, P2, up to PR. Okay, and K are integers greater than or equal to 1. Then phi of n equals phi of p1 to the k1, p2 to the k2, all the way up to pr to the kr. Since these are distinct primes, so this will equal phi of p1 to the k1 times phi of p2 to the k2 times all the way up to pr to the kr. Okay, because none of the other primes are divisible by p1. But we can continue this process and we can keep using the multiplicative properties of phi to see that this will equal phi of p1 to the k1 times phi of p2 to the k2 all the way, if we continue this product, out to phi of pr to the kr. And then we can use the formula for phi of a prime power to write this as each one of these as p1 to the k1 times 1 minus 1 over p1. And we're going to use that formula for each one of these factors. So then that's times p2 to the k2 times 1 minus 1 over p2 all the way out to pr to the kr times 1 minus 1 over pr. Okay. Now if I pull all the prime powers to the front, when I multiply them back together, that will just equal n. So p1 to the k1 times p2 to the k2 all the way out to times pr to the kr. When I multiply them together, that just equals n. So that's where I get my factor of n. And then I see I have all these factors: 1 minus 1 over p1, 1 minus 1 over p2, all the way up to 1 minus 1 over pr. So this would be n times the product over all, or the product runs over all primes dividing n, and the factors are 1 minus 1 over p. So let's use this corollary to evaluate the phi function. So let's evaluate phi of 5040. Well, the prime decomposition of 5040 is 2 to the power 4 times 3 squared times 5 times 7. So by this theorem, this corollary we just proved, phi of 5040 would equal 5040 times 1 minus 1/2 times 1 minus 1/3 times 1 minus 1/5 times 1 minus 1/7. If you think about this, what we're doing is we're subtracting off all the numbers that are divisible by 2. So I need to take off a half of the numbers between 1 and 5040. I need to take off a third of numbers because a third of them are divisible by 3. I need to take off a fifth of number of these numbers because 1/5 of them are divisible by 5 and 1/7 of them are divisible by 7. So that's why this formula also works. So this will just, if you just evaluate this, you get 5040 times 1/2 times 2/3 times 4/5 times 6/7. And when you cancel all the denominators and evaluate this, this will simplify to 1152. So this is much easier than writing out the numbers between 1 and 5040 and canceling off anything relatively prime that's not relatively prime to 5040.